Hello and welcome to this lecture of elements of mechanical vibrations. In the previous lecture we discussed the response to harmonic excitation and base excitation, and later on also discussed how the seismometer is designed, what are the the design issues in the seismometer and how it acts as a simple single degree of freedom system. In this lecture we will continue the discussion on another vibration measurement device, which is an accelerometer, how the design of an accelerometer is done and what are the essential requirements for an accelerometer to work, and what values of the stiffness and damping as well as mass are required for a typical accelerometer. Later on we will get introduced to how the response to a periodic excitation is an important aspect of vibration based design, because there are several cases in practice where the excitation is not strictly harmonic. So, it is essential for us to understand how the response to periodic excitation is obtained. So, a preliminary introduction to this excitation will be given in today's lecture. Okay, having discussed the seismometer design and we have seen how a seismometer is essentially a simple single degree of freedom vibratory system. The other type of sensor for measuring vibration is an accelerometer, and in fact this sensor is most commonly used and it has very wide frequency range as well as measurement range. So, it is best suited and can also be useful where seismometers are used. Of course, seismometers are typically for very low frequency measurements. So, they are common in building vibration, bridge vibration, and so those kind of applications, but accelerometer for mechanical engineering perspective is the de facto sensor which is used. So, it is going to be important and interesting to see how an accelerometer design philosophy is. So, it looks like this, but for us it is important to know what is there inside this casing. So, inside this casing are these parts, like you have a base which you can see. On this base is put piezoelectric discs. So, these are circular piezoelectric discs, and passing through the holes in the disc, these discs are like this, and then through this passes this stud, and there is a mass which is called as a proof mass, and these discs are put in compression. Okay. If you see the cross section, it looks like this. So, you have a base and then a housing here, and between this housing and this heavy mass which you can see here, these piezoelectric discs are between the mass M here and the foundation or the base, okay, a rigid base. Now, obviously, I can consider this entire system again like a spring mass system. Okay. So, this mass is pressed against these discs by using a washer which is screwed on, so that the mass is always pressed against the discs, and there is a reason why it is done that way. These piezoelectric discs are something which can be modeled like a spring dashpot. So, the discs themselves act like a isolation, isolation in the sense that support which you can model as a spring and a dashpot. So, again if the acceleration is an input to the base, the mass will vibrate, and then you can consider this to be a dynamic motion of the mass governed by the parameters of the mass that is put here, that is this mass, and the properties of stiffness and damping of the piezoelectric material. This mass is rigid enough. So, you can assume this mass to be rigid enough, and the piezoelectric material is such that it is relatively softer. So, it will act like a stiffness and damping, and of course, the base and this housing is made of appropriate material, and it is quite rigid in that sense. So, again what you notice here is that this particular sensor, an accelerometer, is also a vibratory system inside. And now it will be important for us to understand that suppose this base is excited with an input y of t, and how do we characterize these parameters of the vibratory system so that we are able to measure y double dot, because the job or the the requirement here from this sensor is to measure input acceleration or the acceleration of any vibratory system. So, you may assume that you have put this accelerometer onto the complex machinery, and you want to know what is the vibration response of this machinery. Okay. You may put this accelerometer on the engine, on the compressors or any other machinery. So, so the idea is whatever is the acceleration, vibration acceleration of the machinery or the structure or a surface which is vibrating is recorded. So, it is to be recorded using a sensor which is in our case at the moment is an accelerometer. So, our job is to somehow design this vibratory system which is a sensor, so that we faithfully record the acceleration being I mean as an input acceleration to the sensor. So, let us look at this particular accelerometer elements. As I mentioned, there is a mass, a mass which is pressing the piezo discs against the base. Now, what are these piezo discs or piezoelectric material? Why are we using it? You all know that what is the property of the piezoelectric material? So, when it is subjected to mechanical strain, it generates electric charge. Okay. So, force, when you apply and generate a strain within this material, the output generated is charge, or vice versa. You input a charge appropriately and it will lead to generation of strain. Okay. So, that is the basic property which is made use of here. So, what is going to happen is whenever this base vibrates with certain amplitude of acceleration, we expect, because there is a mass which is having its own inertia at the top, there would be compression and there is going to be mechanical strain developed. Now, these piezoelectric materials should not be put in tension. The piezoelectric material are always should be under compression. That is the reason why this particular washer or a spring is always tightening the mass against these piezoelectric discs that you notice here, so that it is always under compression. So, even if during the upward motion when the discs get relieved, they are not relieved to an extent that the entire compressive stress is relieved. So, this is how the design of this particular accelerometer is. Now, going back to our basic vibratory motion of this particular single degree of freedom system, we again come back to this model which is representing the physical accelerometer elements, that there is a proof mass m and the piezo discs are characterized by K and C. Now, the input here is x of t and the output is y of t of the mass. Okay. Now, if that is the case, this itself is moving, right. So, how much is the compression in the piezoelectric material? The compression will be y minus x again. Now, this y minus x is the compression in the piezo material. Now, when the piezo material is compressed and generates a mechanical strain, the output is a charge which is taken out. What you can notice here are these leads which are connected to mass as well as to the base. So, from the base or the housing, one lead is coming out, the other one is through the mass. So, the charge basically travels from both ends and then you collect the charge as an output. Okay. So, based on the compression in the disc, the charge is an output proportional to the mechanical strain in the discs. Now, this mechanical strain obviously is will be given by y t minus x t, the dynamic strain y minus x, and the output that you get from these leads is proportional to the amount of strain developed in the piezo disc. Now, if I go back to this, you may notice that there is an output here. The wire actually takes that charge out from here. You can see that. Okay. This stud is a location where the wire is connected here, and then the charge is out from this, and it is processed later on in through electronic circuitry to generate an appropriate voltage or a current. Now, that is going to be the further part of it, but for us for the basic sensor design, let us look at how this output that is being generated, how you can relate it to the base motion, in particular the base acceleration x double dot. Okay. Now, having said this, we do the same thing. We now define a relative motion z between the mass and the base. So, that is y minus x, and then use our normal governing equation of motion for a base excited single degree of freedom vibratory system, and we have done this in the last discussion on the seismometer, that it really turns out to be like mz double dot plus cz dot plus kz equal to it should be minus mx double dot, right. So, having done this, when you substitute for a harmonic base motion, we can talk about what happens if it is not strictly harmonic little later, but assume that the motion being input at the base is a harmonic motion with frequency omega and amplitude x, capital X. So, when you substitute for this x and its derivative into this equation, this is what you will actually get. Okay. So, the right hand side really turns out to be like minus m omega square x capital X cos omega t or e to the power j omega t. And then mathematical manipulations will again yield what z over the capital Z, that is again the solution is now going to be like capital Z e to the power j omega t, that is going to be your assumed response, and assumed input motion is x e to the power j omega t. When you substitute all of these, the ratio z over x would give you this equation, which we have derived many times in the previous lectures. Now, the thing here is that we substitute for r square. So, what we say is that I can write the same equation on the the right hand side, I can rewrite as what? Capital X, what is r square? It is omega by omega n, isn't it? So, I can keep omega square in the numerator, take omega n square in the denominator, and all these terms in the denominator are as they are. Okay. And what is this? This is basically capital Z. So, I am taking this x on the right hand side in the numerator, and r being equal to omega over omega n, I am basically able to now write this equation. What does this mean? That the amount of or the amplitude of this dynamic strain, okay, which is Z, capital Z is the amplitude with which the mechanical strain is going to look like. So, this Z of t is going to look like this, which is y minus x, or in fact y t minus x t, and that is going to be having an amplitude of z. Now, that amplitude or the peak mechanical strain in the piezo disc is going to be equal to this. Can we say that for a given sensor, the entire denominator is a constant value for a given input frequency? Yeah. If you are subjecting it to a particular frequency, then the denominator, particularly omega and zeta, these are constant values. Of course, r will change with the excitation frequency. So, this we can say the compression is proportional to x omega square, okay, and then the denominator is captured in a factor f. We say that this entire thing, we can keep omega n out, but because this part is going to change with the frequency, I am going to write this as f, and of course, you can divide it by a scaling factor of omega n square. Okay. So, this factor is obviously not a constant thing, it is going to be varying if your excitation frequency omega changes. Okay. But suppose you have a particular excitation frequency, then the z or the compression in the piezo pads is going to be proportional to what? This value. Okay. Let us worry about this factor little later, but I can definitely say that it is proportional to capital X omega square. Now, what is capital X omega square? If your x is x e to the power j omega t, then x double dot is minus x omega square e to the power j omega t, is not it? So, this is basically acceleration amplitude. Which actually means that z of t is going to be z e to the power j omega t, and then of course, there will be phase, but then let us ignore for a while that phase. So, and then capital Z is nothing but x omega square f e to the power j omega t. Okay. So, the dynamic strain in the piezo material is indeed proportional to the acceleration, input acceleration, and basically when you take this signal out, that signal is proportional to the strain, because that is the property of the piezo material, that the charge output is proportional to the mechanical strain. And so, this is basic philosophy of the design of an accelerometer, that if you want to measure the acceleration, you need to somehow get this piezo patch to get strained, and that output from the piezo patch piezo disc is going to be an electric signal, which you can calibrate and find out what is the proportionality factor. Now, the $1,000,000 question here is this f factor. Okay. Is this really going to be constant? Because you do not want to keep multiplying with a different multiplying factor depending upon the input frequency. It should be having a linear behavior, that means irrespective of the frequency of excitation, the charge output should be proportional, directly proportional to the input acceleration. Okay. So, let's look at what this factor f is. So, I must make a mention that it is proportional to these three factors. Of course, if you want to write it as equal to, then you will have to account for that omega n square, but then omega n square is only going to scale the things up, it is not going to change the behavior actually. Okay. So, now this f, which is 1 over square root of 1 minus r square whole square plus 2 zeta r whole square, is this a constant function? That is what the question is. And you remember that this particular expression which you have, okay, how does it behave? This is similar to our dynamic magnifier. Okay. It will start with 1, it will go to the resonance region and then come down. Okay. So, if I plot this function, it looks like this. So, if I am going to again plot it with respect to the forcing frequency ratio, and this function is being plotted here for different damping factor. I mean, these damping factors we rarely use in a typical vibratory system, because we know that for all of our mechanical vibratory systems the damping ratio really does not go beyond 0.1, right. But here what we are trying to draw is the variation. So, this is a sort of a zoomed or a region which is in general what we show the variation to be this. We are focusing on the very low values of these ratios, okay, and high level of damping. What you notice is for a damping ratio of 0.7, the curve is almost straight and linear, I mean horizontal up to a frequency range which is given here, maybe 0.25 or so. You see that, which actually means that f is not going to really matter in the proportionality here. Okay. If f is equal to 1 for a certain frequency range, now I am talking about this frequency range 0 to 0.25. This f is going to be 1, and then you can always say that whatever the charge output that you are getting from an accelerometer is going to be proportional to the acceleration, right, directly proportional, and without any multiple. Of course, there will be omega n square that has to be accounted for, but that is not going to change the behavior as such. So, the problem now is what happens if you go beyond this frequency range. Of course, if you go beyond that frequency range, the linearity is no more valid, and then you cannot have an accelerometer measuring different frequencies without making an appropriate scaling to the value that is output, right. You cannot keep on multiplying your output with different values at different frequencies. So, therefore, the measurable and usual operating measurement frequency range will be limited to this point. Okay. I mean, we can say that approximately this is equal to 0.25. Now, when R is equal to 0.25 for the sake of illustration here, what does that mean? Supposing I am supposed to measure a frequency, let us say 5000 hertz, which is going to be 5000 into 2 pi radians per second, okay, just for the sake of simplicity and illustration here. I am saying that from my gearbox, the vibration frequency expected of interest is 5000 hertz. Okay. Now, for that to measure 5000, now I am going to use cycles per second as the frequency, because omega n is also going to be then in terms of in hertz, okay, because the units are consistent now. So, this 0.25 which I got from here, I am setting as omega over omega n, which is R, and my frequency of interest is 5000 hertz, then my natural frequency of this sensor should be how much? Isn't it? 5000 divided by 0.25, that is going to be the natural frequency of my sensor. So, if I am modeling this accelerometer as a simple spring mass dashpot system, then you know that in that small size accelerometer the mass can't be large, right, the way we have in a seismometer. Okay. So, the mass is not too large, so the mass is limited, and for a natural frequency of the order of 20,000 hertz, and maybe if you want to convert this into radians per second, it is going to be even further larger value, right. Such a large natural frequency means what? That the k should be large enough, right. So, this is what the design is, and then of course, for making sure that the C should be such that the damping ratio is 0.7. Fortunately, these piezoelectric materials do have a good damping property or a damping factor, and so that suffices. So, you need to pick up appropriate piezoelectric material and then ensure that the drop in this f value is not beyond a certain range. Okay, that is how your most of the sensors are designed, and therefore, in contrast to the seismometer, which is expected to have a very low natural frequency, accelerometer is on the other side of it, that it is expected to have a very high natural frequency. In fact, some of the sensors are going to have natural frequency 30 kilohertz and 40 kilohertz or so, that means 30,000 and 40,000 of that order. Okay. Then their measurement range can be more than 20 kilohertz, 25 kilohertz. Sometimes you do have requirement that the frequency of interest for measurement can be 10 kilohertz or 15 or so. So, this is the basic philosophy of accelerometer design, and then as I said, this linearity factor is going to be an important deciding factor of its measurement range. Okay. Yeah. And I am going to now pop up a calibration sheet of one of the accelerometer here, and you can notice its frequency response characteristic. You can see that the response or this sensitivity is having a linear behavior, and that accelerometer has a resonance somewhere here, you can notice that. And what is that value? This is 10 kilohertz, this is 20 and 30 and almost like slightly less than 40 kilohertz. That is the order of the natural frequency that a sensor will have, and that will be given here. So, resonance frequencies of the order of 41.2 kilohertz of that order. Okay. And yes, and therefore, the frequency range can go right up to close to 13 kilohertz, 12.8 kilohertz. Okay. You cannot simply imagine measuring such a high frequency using a seismometer, it is not designed for that. Okay, now let us look at how do we find the response to excitation which is not arbitrary, transient or harmonic. We have been discussing the response to a harmonic excitation, wherein the excitation function f of x sorry f of t Okay. So, we have been discussing the response of a simple vibratory system to a forcing function, external excitation, which was assumed to be harmonic. So, what we decided that let's assume that the excitation function has only one single frequency, and by assuming the variation of the force to be represented by e to the power j omega t, which actually means that it is let us say a harmonic time function, okay, at a particular frequency of excitation. So, essentially the right hand side of our governing equation of motion was a harmonic single frequency, obviously forcing function, right. Now, in practice there are situations where the excitation function need not be necessarily a single frequency or a harmonic forcing function. Now, the examples of that is this. We assume that this cam, which was exciting this tappet valve mechanism of an IC engine, we assume that the excitation at the base here or the movement at, if we define this to be, let us say y of t, okay, the excitation at the base was harmonic. So, with this excitation y equal to capital Y e to the power j omega t, we assumed it to be harmonic, and then we basically went ahead in finding out what is the response of the vibratory system. Now, this is very important, let me tell you, and you will realize shortly why we made this assumption, despite the fact that many times the cam may not have a profile. You already have learned in your kinematics and dynamics course that a cam profile can have different forms, right, and the form is essentially guided by its intended dynamic characteristic of the cam follower mechanism. It should not have a heavy jerk and so on so forth. So, the profile of the cam would not really generate a base motion of the follower which is harmonic, right. So, this particular assumption of us that the base is going to move with a harmonic pattern or a motion is really not strictly valid in all cases, of course. In many of the situations we have discussed that yes, we can assume the excitation to be harmonic, and it suffices. For example, all the rotating machinery by default will always have unbalance as a sort of a residual unbalance exciting the dynamic system. So, the harmonic excitation function in terms of the force acting on any rotating equipment is definitely going to be there. So, harmonic excitation case is definitely very important and practically relevant as well. But in some situations you do get the excitation function which is not harmonic at all, right. For example, this cam, although is shown here like this, is not going to be strictly having a harmonic profile as we discussed it. We know we have learnt about cycloidal cam profile where it has the best dynamic characteristic, and therefore, the profile it will generate or the excitation function that it will generate is not going to be harmonic, right. So, when it is not harmonic, how do we cater to that kind of a situation? How do we account for that situation? How do we find the response of the system to such kind of an excitation is what we are going to discuss today. Now, so that is one thing, and particularly in the context of this particular application where the valve is supposed to open and just before the power stroke should be or before the compression stroke should completely shut off, right. So, the motion of this follower is typically expected to have a different kind of a cam profile. So, as a hypothetical case or a slightly this kind of a abrupt change is of course not designed most of the times, but for the sake of illustration here, what I am saying is that the valve will open gradually as the cam rotates in this particular fashion counterclockwise, and then it will push the follower up, and the mixture of the fuel will let in gradually, and then during the compression stroke we expect that the valve to close as fast as possible. So, there will be a sudden closure of the valve, and then there will be no movement of the valve till the next cycle begin, right. So, this is typically the requirement from this cam and follower mechanism. So, supposing that if the cam profile is something which you see here in this particular case, then what would be the base excitation to this follower system? Now, that base excitation can be easily approximated by this kind of a variation of the motion, okay, the base motion with time, right. So, it will gradually open and then suddenly close, then again keep opening and closing. Of course, there will be some dwell period, but for the sake of illustration here, we can broadly consider that the cam profile will be such that the motion which is imparted to the vibratory system, in this case our vibratory system is this, and this is almost like a base excitation from the cam. Now, is this a harmonic one? This entire thing is not harmonic. So, when we write our governing equation of motion, that mx double dot plus cx dot plus kx equal to y of t, this y of t cannot be written as a harmonic function of time, because the motion is not harmonic, it is in this case a sawtooth kind of a profile. Okay. The other example is, let us say, again an IC engine in this case, with a crankshaft connected to a huge flywheel, and just assume that this engine is a 4-stroke engine, single cylinder, and you all know such kind of an engine will be subjected to excitation torque, will it not, as a function of theta, angle theta rotated. Okay. Now, if this flywheel is having a larger inertia as compared to the inertia of the engine, okay, if this flywheel inertia is large enough, as an approximation I can presume this to be fixed, and then I can model this as a single degree of freedom torsional vibratory system, which means that this engine inertia will be the only inertia, assuming shaft or crankshaft to be massless. So, this will be contributing to the stiffness, and then I will have to figure out what torsional stiffness this shaft will offer. Now, if this theta is the only degree of freedom, I know that the natural frequency of this system is going to be square root of kT over IE, right, and that is basically the single degree of freedom system. Now, if I want to find out the response of this system to such kind of a dynamic torque developed at the engine because of the functioning of the engine, there will be a power stroke, there will be compression stroke, suction, exhaust, and so on. Now, in a cycle I will have to then represent this T theta as an external torque, because the power stroke is going to excite this entire torsional vibratory system, okay, into vibration. Can I write this T theta? So, again maybe I can write the governing equation of motion the way I wrote it for the base excitation case. For this case I can write the governing equation of motion. I hope you would agree with me that it would take this kind of a form. Instead of theta, it is a function of time. Theta for a given constant angular rotational frequency omega would be related to t. I mean theta is nothing but, I mean I can write or replace theta as t, because what is theta? It is omega t, and omega being constant angular rotation speed of the engine, for that condition this equation is perfectly fine. So, what I am getting here is the right hand side term, which is an excitation torque, is a function of time t. Can I write this t as a function of time as some constant torque e to the power j omega t? I can write this provided I know that the torque is going to vary harmonically, and then the same governing equation of motion and everything associated with it is valid. In fact, I may need to add the damping or a dissipating term, but you can add that as a to make it more complete by including the structural damping of the crankshaft I can add Ct theta dot as the dissipation term in the equation, but that does not answer basically the question that I am trying to pose or ask is it valid to have a harmonic excitation torque being considered here for solving this particular problem. Now, again recalling all what you might have learnt in your kinematics and dynamics course is that, or even in probably in some other subjects related to IC engines, you must have have a clear idea that the torque which is acting because of the operation of the engine on the crankshaft may look something like that. Okay. So, during suction, during expansion stroke, there is a huge increase in the torque generated on the crankshaft, and comparatively in the rest of the strokes there is hardly much of a generation, and it is expected to be so. Now, is this a harmonically varying torque? No way, is not it? So, now if this is not the case and t as a function of time cannot be expressed as a harmonic time function, I will have to figure out how do I find the response theta t. That is all what we are trying to find out, what is the angular twist or a dynamic twist in the crankshaft. That is what the whole purpose of our vibration analysis is, that given certain speed and operating conditions and the torque being generated at the engine, what is the maximum twist the crankshaft is going to get subjected to, and whether that assuming that this vehicle is going to work for 10, 15, 20 years, is that going to create a fatigue failure in the crankshaft. You can imagine what will happen if there is a sudden failure because of the crack being generated and suddenly things are going haywire. Okay. So, this is all the purpose of this vibration analysis, is to figure out what is the implication of these amplitudes theta t onto the stresses and therefore the life or the durability of the product. The other example that I might like to give you here is in steam turbines. You know that there are blades which are on the periphery of the shaft, isn't it? Steam turbine or even the hydraulic turbines, and then the fluid is flowing in through the nozzle, or they could be flowing through the guide vanes, right. Now, if you consider the movement of these blades, whenever the blade passes across this nozzle, what is going to happen? The fluid is going to impinge on the blade, right, and that entry or that fluid impacting on the blade, however nice you design all the inlet angle and the profile of the blade, there will be some sudden change and the force will act on the blade. So, once in one rotation, if you focus only on one blade, because one blade itself is a vibratory system, it is a cantilever, is not it? A blade is nothing but a cantilever in action. Now, assuming that, think about that blade making one rotation. So, in one rotation, each blade is going to get subjected to how many such pressure perturbations or force impacts? 3 times, depending upon the number of nozzles. In this case, you see that there are 3 nozzles, okay, equiangularly situated. So, now if I consider a blade to be a vibratory system, then this force as a function of time again is no more a harmonic force, isn't it? It will look like this. In one rotation of the shaft, each blade is going to have 1, 2 and 3 excitations. It may not be as abrupt as you see here like a rectangular pulse, but it is an approximation that something similar to that will get acted on the blade, and this will continue over a number of revolutions, right. So, is this a harmonic force? No, right. So, my governing equation of motion f mx double dot plus cx dot plus kx equal to f naught cos omega t or f naught sin omega t or f naught e to the power j omega t is really strictly speaking no more a valid assumption. So, we will therefore now have to look at how do I estimate or evaluate the response of a vibratory system to a force or excitation function that is not harmonic, but periodic. Now, you all understand clearly that there is a difference between a periodic excitation and a harmonic excitation. What is the difference between the two? Right, we have been discussing that our excitation is harmonic, which actually means that it is a single frequency excitation defined by cosine omega t or a sin omega t, whereas if I show this excitation to be like this, okay, or even like this, what is the difference here? The only difference is all of them are having the same time period, please make a note. Okay. So, the point is that these excitations functions, they do repeat after the exactly same period of time. Okay. So, they are in a way periodic, right. They may not be harmonic, but they are periodic because there is a definite period of repetition of these excitation force. But it does not follow a harmonic function of time, right, it is different than that. So, here we now have to explore how do we evaluate the vibratory response to such a periodic excitation where there is a definite period of repetition. Only thing is the function that defines the mathematical function that defines this variation of f as a function of time cannot be simply written as a single frequency function, a harmonic function or a cosine or a sine function, right. So, this is precisely what we are going to look at. Now, you all have must have learnt in your mathematics course that a periodic time function can be decomposed, okay, into its constituent sinusoids. Okay. So, you may imagine this kind of a periodic function. You can see that there is a definite period of repetition to this periodic function. Okay. So, it is perfectly repeating after a period of capital T, in this case maybe 0.05 seconds. So, I can decompose this periodic time function into its constituent harmonic time functions. Okay. So, in this particular case it is made up of two sinusoids, each with different amplitude. Okay. So, this one is different and this one is different with two different amplitudes and two different frequencies. This one is having a frequency of 20 hertz and the second constituent is 40 hertz. If you mix them in time, you know, simply algebraically add this value and this value should be at the same time, then you get this value. You add this value, or maybe I should say maybe I add this value and to that I might use this add this value same time, I should get back this particular value and so on. So, basically you can algebraically add two sinusoids with their individual amplitudes and their individual frequencies to make up the original time function. Okay. This is precisely what Fourier series decomposition is. Okay. That any periodic time function can be decomposed into its constituent harmonics. And there is of course a requirement that the fundamental frequency would be related to the original time period of the original time function f of t. We will discuss that part, and then its constituents are basically integer multiples, the frequencies are integer multiples, but I hope you recollect Fourier series decomposition, and that is what we are going to use. Now, this if you see these constituents, these two constituents added up, and if you look that added signal from the time axis orientation, you get a time domain data or a time domain function f of t, right, f as a function of time. But if you see this decomposition from the frequency axis, okay, you get what is known as the frequency spectrum of the same signal. Okay. If I look at this decomposed signal, the first constituent and the second constituent with their individual amplitude, as I mentioned here, A1 and this A2, would appear as the two distinct frequency components in the frequency domain signal. So, this spectrum or this frequency domain signal is a frequency domain representation of this original f of t, the time domain function. Okay. They are equivalent, and you can convert from one to another using a mathematical operation. Okay. Now, what is the relevance of doing all of this or discussing all of this is that the moment I can decompose this signal into its component harmonic constituents. Okay. Please make a note, what is this? This is a pure harmonic signal, this also is a pure harmonic signal. The Fourier series decomposition allows us to decompose or represent the original time domain function into its constituents harmonic functions, which clearly means that I have two distinct, in this particular case two distinct, but there could be many more if the function is such. In this particular case, I have created a function which looks like what you see in the black colored plot, which is made up of only two harmonic time functions. So, I get its corresponding two harmonic time function. The moment I get that, what I can do is that I will treat the system to be subjected only by this particular harmonic time function, in this case this let us say f1 of t, and then I will evaluate the response. Okay. And later I will independently assume that, I mean I will assume that the system is also independently getting subjected by another forcing function, a harmonic forcing function f2t. Right? Does that make sense? And I will then find out response because of this harmonic forcing function, and then find out separately the response due to this harmonic forcing function, and I will simply add them up. Can you tell me what will be an underlying assumption if I want to do that? Okay. The system is assumed linear. Okay. The moment I assume the system to be linear, I can invoke the principle of superposition. In this case, I will say that response is made up of two responses individually obtained by assuming an individual forcing function. Okay. Two different forcing functions, but I can add them up because the system is linear. Okay. So, the system with the assumption of linear system, I can then decompose any periodic forcing function into component harmonics and find out individual responses, and then simply add them up. That is what we are going to do in this particular case. Okay. So, coming back to this Fourier series, just a slight recap of what this Fourier series is. Any periodic function can be expressed as an infinite sum of pure sinusoids. Now, a mathematical statement, and for the illustration I am showing you a periodic time function, just like the sawtooth profile that we saw for the CAM excitation case. Now, this will be expressed, this f of t will be expressed now, as I said, as an infinite sum of component harmonics or a pure harmonics or pure sinusoids. Now, this is what the series looks like. It has certain amplitude corresponding to what particular term that you are talking about, 1 to infinity. So, the first term will be a1 cos omega naught t plus b1 sin omega naught t. The second term will be a2 cos 2 omega naught t plus b2 sin 2 omega naught t, okay, and so on. This will continue. There would be some static part of the or a constant amplitude part in this series, which is defined as a naught, and it will appear non-zero for all functions which are not having 0 mean, which is obvious. Okay. All right. Now, the question will be, what is omega naught? We have expressed this as a summation, right, summation for 1 to infinity. There appears to be so many unknowns here, a n, b n, what is omega naught, what is a naught. So, omega naught is related to the period of repetition. So, omega naught is going to be equal to 2 pi over the period of repetition. For a harmonic time function, we have seen omega naught will be equal to 2 pi by capital T, where T is going to the period of the cosine or a sine function. What is a naught, a n and b n? So, these are the coefficients which depend on the function itself. Okay. This you might have learnt in your earlier courses. So, the coefficients a naught, a n and b n are obtained by using these integrals. I need not go into the details elaborating how they have been obtained, but you must be familiar with this from your mathematics course. Please make a note that these coefficients therefore depend fully on how your time function, original time function f of t is. Okay. That will guide and decide what are a n's and b n's and a naughts. Okay. Omega naught is defined for a given periodic function, and f of t is what this function is. So, ultimately if I want to replace the original time function by its component sinusoids, then I need to capture this f of t in a mathematical form and evaluate this integral, so that I know what are their individual amplitudes. In the previous slide, if you remember, you definitely would like to know how much is this amplitude and how much is this amplitude. Frequency, of course, you can get by using the expression that it is 2 pi over period of repetition. You know from the time domain data itself what is the period of repetition. So, omega naught is anyway known, and this second frequency is always going to be n omega naught, right, n omega naught. For the second frequency, it is going to be 2 omega naught. That is why if the first one is 20, the second one will be 40, the third one will be 60 and so on. So, once this is done, I need to now have an idea that how do I capture f of t. Now, of course, another way of writing this function is this, that you have the two cosine the two harmonic functions clubbed as a single expression. We all know how that can be obtained, but this can be written in a more compact form like a n cos n omega naught t, in this case minus phi n, and that a n is a n square plus b n square from this expression, and phi n is defined like that. So, this is something which is quite simple and straightforward. So, either you use the first one or you use this one, that is one and the same thing. It is basically the two harmonic functions are accounted for by the amplitude and the corresponding phase. Okay. As I said, omega naught is 2 pi by period of repetition. Now, the question is, if I want to evaluate these coefficients, I need to capture f of t in a mathematical form, so that I can integrate this expression. So, that can be obtained by looking at your function, right. So, what is our function here? It is this sawtooth function. Now, instead of this particular function, if you recall the base excitation in a cam of an tappet valve mechanism, wherein the displacement was with the amplitude capital Y, and the motion was as a function of time y of t. So, it started lifting the cam the follower straight like this, and then suddenly the valve closed, and then again valve opens and closes, and this is the way it goes. Now, for us the function has to be defined for its period. So, the period is this much. So, I need to define this variation by the function f of t. Now, obviously, it is quite easy and simpler. So, it is quite simple to use the function y of t given by this capital Y by capital T into t. So, t is any time at which I want to know what is the value of that function, and that value of the function y at time t can be easily expressed mathematically as a linear function of that slope. Okay. So, capital Y by capital T is the slope of that line times the time at which I want to find the value of that function is simply a simple expression like that. So, if I want to find out a n, I will simply integrate it by substituting the value of f of t, which is going to be in this case capital Y by capital T times t cos n omega naught t dt, and you know how to evaluate this integral is quite straightforward that way. Okay. And I can find the amplitude a n by substitute. Once I get the expression of a n, I can substitute for the value of n equal to 1 to get value of a 1. I will substitute in this expression the n equal to 2 to get the value of amplitude 2, and so on. Once I get a n and b n, I can get this amplitude, and then simply I will have a complete idea as to how many harmonics and how many their corresponding amplitudes to be obtained. The summary of this lecture is that we discussed how accelerometers are designed, what are the desirable stiffness and damping parameters of an accelerometer as a vibratory system for an accurate measurement of vibration acceleration. Then we discussed the periodic excitation case. It is discussed that the periodic excitation is actually a summation of harmonic terms. In that context, we got introduced to the Fourier series, although you all are already aware of Fourier series. So, these are the recall questions that you can now attempt based on what we discussed in today's lecture. And these are the answers.